Okay, I'm live now, so.
Okay, I'll shut my mouth.
Let me see if everything's. Is it inverted? Oh man. And two of my friends, apparently.
Nice.
Yeah, that's pretty sweet.
Yeah, you've got time afterwards. And that's a big if, because you might just want to celebrate for a while. I'm excited about like 4 different things that we're talking about.
That's good.
I want to share things. Big if, though.
Yeah, I don't know if I want to just print my thesis today and just get over it done with. I feel like that's impossible, so I might come back up again next week.
All right, but even
Yeah.
if, yeah, just let me know.
Yeah.
Yeah, I'll see if Tracy remembers that we might possibly have a meeting today. I mean,
At 1?
yeah.
Okay.
I'm crossing my fingers, but I guess I could just work something out there.
Yeah.
I guess I'll just assume that I'll have to work something out with her.
Did you need to talk to her?
Okay, need is a, not need to, want, yeah.
Okay. Okay, I'm gonna get thesis forms. Oh man, just no, this is not too bad.
Oh,
Just get it later.
okay, I can get it.
If you want.
All right, watch out for this guy.
How's your part 3?
Oh, it was surprisingly not bad at all.
Yeah? What do you get
It
on
was
this?
honestly a little disappointing. Well, because I felt like it didn't feel right because Bob asked the same lambda hyperon question.
What? Okay.
Exactly. That when I heard that, I was like, have I cheated? I mean, is this? I guess not, but it didn't feel right. And then by the time we got to something new, I didn't know how to answer it. He was like, "That's okay. You've answered enough already."
Oh.
That's not true. So that was fine. And then Barton's question was so easy.
What did you ask?
He said, it was so sing-song too. Let's imagine you have two scalar particles and one decays into the other. What's the constraint? Could you write up the free Lagrangian? Oh, sure. And he said,
For a scalar?
Yeah, two scalars.
For two scalars?
Yeah.
Oh, like the general?
Phi and psi.
Uh-huh.
Okay, I can handle that. Then he said, what's the constraint on the masses if one is to decay to the other? I'm like, M is greater than 2M. He went, very good.
Nice.
It's confusing. And then he said, now let's write up an interaction that would lead to this kind of decay. Okay, 3 point. He went, yes. Hey, how you doing? Not bad.
Good to see you again.
Good to see you again. Yeah, so was it just a coincidence that you were around at this point, or?
Oh, it's a happy coincidence, I guess.
Yeah,
It happened before workout, so I've come. That's what you're asking.
wow. Not as direct.
You cut your hair.
I did. It was so hot. And because my brother's getting married.
Oh,
and
congratulations.
Yeah. We're all surprised. And his fiance said, you better get it cut for the
Really?
pictures. And I went,
Wait, when's the wedding?
end of June. Yeah.
Are you flying out Wednesday? Or
It's
are you
actually,
coming back?
they're coming back just to Baltimore. So I'm going to drive through Princeton on the way down.
Oh.
Yeah. So you're perfect in every way. Oh, yeah.
Or
Do you like
that
that?
top?
What?
You burned
Yeah,
that
yeah,
top.
Yeah.
Thank you.
Yeah,
Do you want me
thanks.
to use my iPad?
No, it's fine. I'm all set up here. Yeah. Hey,
What's
you
it
can
look
come
like?
and see. It seems fine.
Is it gonna be online?
Yeah.
Who?
Kai Chung and Edwin.
Where?
There you can see.
Oh, I can't see them. Hello.
The thing is inverted, right? And I thought I was
What do you
just,
mean?
I was like,
Oh,
this is
yeah.
nuts. But actually, it's okay.
As in they can see it though, right?
Yeah,
They
it
can
is.
read
It's fine.
This is what you're reading. Okay, nice.
Yeah.
I can hear everything.
Yeah, they can hear everything. It's live.
It's okay. It's funny that they can see us, but we can't see them.
Yeah, that's very weird.
Okay, so you can sit right here at the panel.
Yeah, the panel will be here.
It's very close.
You can move back if you want.
Okay. Okay, how are you feeling?
Okay. I'm gonna see slides that I don't recognize.
Okay.
Sure of it.
That's great.
You don't okay.
Yeah.
You've been hanging out with them for the last couple days.
Who? Oh, these?
The
slides?
slides?
Yeah.
No, actually they didn't exist until last night.
Whoa.
No, some of them, yeah. I mean, I make them and then I go on to the next one and I make like I just never look back really.
Wow.
Yeah.
So they could be redundant too. 3 of the same slide, just forgot.
No, not that bad.
Well, now, I mean, I keep saying this, but I really can't wait to see that point where you're like, moving on. No, it's really good. On the last question was from Will, where it's just like, what the beta function and how do you measure alpha as stuff. And so then that was.
No, I actually don't know how to measure alpha S.
Exactly, neither did I, but he
Uh-huh.
guided me through. Oh,
How do you
deep
measure
inelastic
alpha S?
scattering.
Sorry?
Deep inelastic scattering, measure the running of things.
Huh?
It's a,
How do you get alpha S from DIS?
It's a loop between two chords.
Oh wow.
Yeah. No, it was bad because I guessed, I was like, maybe it's DIS. He went, let's think about that. Oh, what have I done? But then I asked one of the others, and they said, oh, he forced me to go there.
Oh, I see. Okay, so it's like a one loop correction to DIS.
Yeah, yeah.
Interesting.
And then the thing I just couldn't get was that the part-time PDFs, that's redundant, also had a running, and so then you had to use that also. So I still don't understand how it works, but I'm pretty sure it does work.
Okay.
Yeah, there was so many points.
Interesting, yeah.
At one point, he just kind of gave up. He said, all right, you're fine.
And that's usually how it is.
So you're talking to the tech companies around here, huh?
Yeah.
Biomed.
Bedtime. Trying to.
It's gonna be. You talk to a lot of different people.
Night.
No, just like for your job. It's not. You
Yeah.
don't just hang out with the same crowd every day.
Yeah.
You don't get to get comfortable like Hongwan. But
Well, we've talked to a lot.
okay. Well, that's true. Yeah. That's true. I wish everybody thought like that, but it's not just clothes.
I don't know. I get it.
I don't know.
Yeah. Yeah, it's fine. It's fine.
There's a way to keep it. And it's usually just a kiss out. And it should be right by
That's pretty light. It's okay.
No, okay. We've got time to burn. Okay. Yeah.
Well,
I think so. They rewarded a 20% off.
well,
I just need to get my parents.
Oh, really?
I don't know.
They're not connected?
No, I can get them. Oh, my mom says.
My mom's sewing.
Oh, okay. Yeah. Mm. Yeah, we can't hear anyone.
But you can see who's. Can you see who's online?
I can see that there are 5 people online, but
But you can't see who. They
I
are.
can't see who. Yeah.
So it's gonna last an hour, right?
Yeah, about the.
Must stay to the end.
No lah, don't need.
Let's stay there.
No. I mean, if you have to go, you should.
Acknowledgements are at the end, right?
Yeah, unfortunately. Yeah, I can't start with the acknowledgements, right? Hi. Hi. This is my wife.
Thanks
Thanks for coming.
Good
Thank
luck.
you.
Good luck. Good luck.
Thank you.
So I can just practice in the back.
Yeah, please. You can sit
Yes.
anywhere you want. Yeah. No worries, yeah.
It's quite challenging to get here.
I know, yeah.
I think it's number 1 and number 6 for spot.
Yeah.
They don't know where to go. Anyway,
Oh, man.
I'm glad you found it.
Perfect.
Yeah.
Should I see the back?
You don't have to sit anywhere you want.
So that's
Some people find it that. No. Seriously, no.
good.
I'm gonna take my foot out of my mouth. All I'm saying is I've noticed at these events is usually the back because they want to keep their distance from these people. When did you pick your? Do you pick your committee, or do you just pick one person?
I picked Jesse, and then Justin is picked by Ian, I think.
Okay.
Yeah. So it's a mix. You get 2 theorists and 1 experimentalist.
Did you?
But your committee will be huge,
Oh,
right? It could be like 4.
seriously?
Yeah.
Like how +1 becomes huge.
Yeah. I mean,
No,
3 is a normal, 4 is.
Yeah. I don't know.
Yeah.
Did you pick Jesse before you knew that you'd be doing the tabletop part with him? Or was this kind
I was already
of
talking to
force?
him.
Yeah.
Yeah.
Take ownership.
I mean, he is the closest.
Oh, of
person
course,
here,
yeah,
so,
makes sense.
Yeah.
Anyway.
Hey,
Good luck.
thank you.
Hello.
Just so free, such a free spirit. It looks like he just came in wandering. Yeah.
Maybe he did.
His office. That's gonna be the last we see him. He's not coming back.
Fine.
Do you want to be recorded?
That's a yes.
It's gonna be one of my worst talks ever.
That's a yes.
Yeah. It's gonna be pretty bad.
Just use your laptop to do it too.
I don't know how to do it. Hi.
You can use.
How's it going?
Good. I
Good.
give myself extra time to get here because
Yeah.
I always get lost
Oh, in
when
the
this.
CTV?
As soon as it's a 6C.
Hey.
Hey. Good luck.
Thanks. What?
No.
Talk. Oh. Oh, wow, okay. Jeez.
How much income would you have?
I don't know.
You notice that there's a sleeping man up there. I spoke. That's Patrick.
Yeah, he was sleeping here.
That's
He came in.
Well, I don't know. 'Cause he
Yeah.
we couldn't get any information. It's just so
Why does he have a yeah.
He was in my office. I walked in this morning. Like, I hadn't seen him all semester. He's on the ground sleeping.
He was in your office?
Yeah, but he's my office.
Oh, yeah, that's right. Yeah.
I wasn't expecting some sort of creature on the ground when I walked into my office.
And then at some point you moved up here.
Yeah, I think I startled him.
Oh.
I haven't started.
Well, it wasn't really
Okay.
it was dark. There was
Okay.
some-
Yeah, you look
so
Okay, okay.
moving.
No, that's fine, it's fine.
Okay. Dave's pretty adamant.
Hey. Hey.
No.
Yeah, congratulations. Hey, hi.
Yeah. Could have been involved in my parents.
I didn't know.
No.
Good.
Yeah, I don't know what it is.
Are you set up for your parents to?
Yeah, right here. Yeah.
Okay. Jesse doesn't show up. Go down and show up.
Okay, yeah, no worries. I can do it.
He's chatting with Cliff Jones. So.
Oh,
I'll just pop that together.
You see Bernie.
Well, having a committee member late is better than mine. So at Caltech, it's closed door. So it's just your thesis committee. And I was on Atlas, and the head of US CMS was on the committee. And he came in with my thesis printed out
Oh wow.
with like 100 Post-it notes, little tabs.
Oh my gosh.
And he said, "Don't worry, I'll just ask questions as you go along." And in the end, it was all obviously totally fine, but I was like, "Well, that's mildly intimidating."
Uh-oh. I got locked out of here.
I'm just gonna run to the bathroom.
Oh yeah, no worries.
Just remember that.
What?
No, I just.
Oh, it's your fingerprint, yeah. Hey, congratulations on your award.
Oh,
I
thank
saw
you.
it, yeah. Wonderful. Oh yeah, what was that
I
about?
don't know. She got it right for the body. No, the good win. Teaching award. Good win? Yeah, good win. Oh. Yeah, because I sent out an email about it. It said, in return. I hope that was just out of the way. Yeah. Actually, I'm surprisingly often for some reason most people like write tuner.
Tuna.
Tuner. Because it's just missing an R. Yeah, right. Yeah. Turner is like a complete modification. Jiren from my name. It's just a different conjugation. So you're turning right now.
Just you can hear it.
Oh yeah, no.
It was good that I went down because he was engrossed in a physics discussion.
Oh.
So, yeah. Guess you will be him.
Oh, really?
You're not good, yeah. But he was having a good chat with Cliff Chung and looked completely like, oh wait, is it 11? And I walked in the door, so I think it was good that I went down.
Yeah. I was telling Hongwan I'm having a committee members leave in my defense, so at Caltech it's closed door. And the head of the OCMS was on my defense, because I was an Atlas thesis, and he came with my thesis printed out with like 100 little post-it tabs. And he just said, "Don't worry, I'll just ask you questions as you go along."
When I scheduled my thesis defense, I made the mistake of having both Lisa Randall and the head of carbon astrophysics on my thesis committee.
Which meant it was impossible to schedule.
Yeah, so when I first tried to schedule it, I was like, oh, it's like early March, I'm scheduling for sometime in May. This is plenty of time. I ended up defending it like mid-March.
My apologies.
Oh, no worries.
Yeah.
I'm on sabbatical. I didn't realize.
Time doesn't
Space.
exist.
What is this about?
Sorry, Craig. Where's the thesis?
Yeah.
Pull it up. Sorry. Yeah. Just 1 second.
Hello. Good. You're alive.
I'm alive.
Yeah.
you want to just
haven't
download
seen
it?
you.
Oh yeah,
You've
yes please. Yeah.
been off the
Yeah,
campus.
both Tracy and
Oh, no, yeah, you're
I know. Yeah.
which is remarkable.
Yeah.
This is so many questions now.
Awesome. Okay. Good. Yeah. Great. Thank you. Yeah.
All right, so today we're going to hear from Hongwan Liu about his thesis work on dark matter energy deposition and production from the tabletop to the cosmos. We'll first have the open section of the defense where Hongwan will tell you all about what he's been doing. You should feel free to ask questions during this period.
Yes, please. Yeah.
I will, at the end of this, we'll ask everyone to leave except the thesis committee. We will have a closed door session and then we will make a decision. Let you know. Take it away, Hongwan.
Thank you. All right. So today I'm going to tell you exactly what I've been doing over the last 5 years, I guess. Basically, I've been thinking a lot about looking at dark matter, trying to figure out exactly what it is. And the way that I like to approach this problem is to figure out what kind of interactions could you have between dark matter and all of the known particles in the standard model. So in other words, the particles that we know of today. So generally, the approach that I want to take is to figure out, is there any way that dark matter can deposit any energy in the form of standard model particles, or can it bump into standard model particles like protons and electrons and deposit a little bit of energy that we can then detect? And also, how can we produce dark matter? So if there's some kind of interaction between dark matter and regular matter, we might be able to produce it at very high energies. And also, dark matter is around today, and as I'll show you later, there's tons of evidence for it. And one of the questions that comes with that is to ask, how did dark matter get produced in the early universe as well? So that's a very broad overview of my thesis, and then I'll tell you a little bit more in detail as we go along. Technical problem. There we go. Okay, so I'll begin to talk by giving a very brief introduction to dark matter. I promised a lot of people that at least the first 10 slides will be comprehensible. So the first 10 slides, and then we'll plunge into the horrors of the stuff that I did. So before we begin talking about dark matter itself, let's think about what we know about the solar system. So this is the solar system. The sun is in the middle, which is something that sometimes gets debated, but it is true that the sun is in the middle and the Earth goes around it as the third rock from the sun. And then further out, there are other planets like Jupiter, Saturn, Uranus, and Neptune. There used to be Pluto, but now it's gone. But this was a picture that essentially took 2,000 years to figure out. And we won't go all the way back to what it was 2,000 years ago, but just to 1846. And if you just notice, I erased Neptune from there because in 1846 we really didn't know that Neptune was there. But at this point, we were doing a pretty good job in terms of astronomy. There were lots of people making observations of the stars, and also by this time, Isaac Newton had come and gone, and so we were relatively confident in our abilities to do calculations involving gravity and so on. So at this point, we understood gravity. We didn't know that Neptune was there. How did we discover Neptune in the first place? And the answer is by looking at its closest neighboring planet, Uranus, and plotting essentially the orbit of the planet. So you think you know gravity very well. You know the sun is in the middle. You know that there are all these planets that are revolving around the sun that you can observe. And from there, you can say, okay, I'm going to look at the planet, Uranus, and I'm going to figure out how is it orbiting the solar system, and does it agree with what we know should be true from Newtonian gravity. So you can do that, and it was done by an astronomer called Urbain Le Verrier. And if you just plot the observations versus where you think it should be, you get what we have here on the left. And you see that this is on the x-axis, it's a label of years. So starting from 1700, 1750, 1800, you can plot the difference between the observed orbit of Uranus and what you actually computed. Okay, so if what you computed is the same as what you observed, then you'll see that everything should lie on this line here, which says 0. But obviously it's not 0, you get deviations, and you can see these deviations are pretty large. So what happened was Le Verrier went out and did the measurements and said, something is wrong with the orbit of Uranus, and what he decided was that the reason why you were seeing these discrepancies is that there's another planet out there that you call Neptune. And based on that prediction, he managed to convince an observatory in Germany to actually go out and look for it. And in the end, it was observed by Johann Gottfried Galle, and as well as his graduate student. And since this is a PhD defense, it has to be in bold, italicized, and underlined. The graduate student is Heinrich Louis Starres. And you can see here what they observed. Just going to grab a stick for that point. So what they observed was basically, just look at the stars. Do you see any stars out there that was kind of unexpected. And you see here, this is where they observed the star to be that they didn't realize was supposed to be there. And this was the predicted calculation by Leverrier. And I mean, it's pretty good reading, at least by the standards of the time. And there was actually also another prediction by John Couch Adams that was way out here. And unfortunately, even though he did make a prediction, he doesn't get the credit just because he was like several degrees off. But yeah, so the overall story that I'm trying to tell here is that if you think you understand gravity well, right, which at this point in time, people thought they did, and I mean, even by today's standards, the way that they understood gravity was already pretty good. You can make predictions, and you can see if things are orbiting in the way that you expect them to be, and if they're not, then you know that there are additional objects out there that are exerting an additional gravitational pull that you didn't know about. And just from the gravitational effects, you can deduce this. So, discovered in 1846, but we had to wait till 1989 for Voyager 2 to actually go up to Neptune itself and take this really amazing picture of the planet. So again, this story is discovered gravitationally, and then we visited it in 1989. There's a gap of 140 years. So now let's turn our attention to dark matter, and really the dark matter story is very similar. This is the Milky Way. You can, on a very dark night, you can actually see a band of stars that looks like a bunch of dust in the night sky. And this actually turns out to be a galaxy. And a galaxy is just a collection of stars that are gravitationally bound together. And the thing that you see in the night sky, this beautiful picture, it's actually a side view of something that looks like this spiral galaxy here. And this star here that I've indicated on this picture is where the sun is. Obviously, we can't actually take a top-down photo of our own galaxy because we're not spacefaring and so on. But this is what we think the galaxy should look like. And so we can do the same thing, right? We can look at the galaxy, we can pick out some of the stars that are in the galaxy, and we can watch the stars orbit around the center of the galaxy. We can see that there's a bunch of stuff in the center of the galaxy.
I'm just considering lowering the shades.
Oh, do you want to lower the shades?
Yeah, can you bring the shades down?
Yeah. Sorry, people in the back. All right.
Yeah, I think that's better. Thank you.
Yeah, no worries. So yeah, as I was saying, you can look at the stars in the galaxy and you can observe how they're rotating around the galaxy. You can see all this bright stuff here, so you can estimate how much stuff is in the middle of the galaxy and how much of it is actually pulling on the stars as they go around. And you can, make a prediction for what you think the orbital dynamics of these stars should look like. And just based on what you can see in the visible wavelengths, you expect that the velocity of these stars goes to something like this dashed line. But it turns out when you actually do the observations, you get something that's closer to this curve here. And so there's a huge discrepancy here. And again, we think we understand gravity very well. It is one of our most well-tested theories that we have. What this is telling you is that maybe there's something else somewhere in the galaxy here that is pulling on the stars, that is exerting this additional gravitational effect that you didn't know about. And this thing is exactly what we call dark matter. So this is the usual way of introducing people to the fact that dark matter exists, that there is an invisible gravitational pull by something, and we should go out and look for it. Right, so you can see here, this is exactly analogous to what we were doing for Uranus as well. But as I was saying, aside from this rotation curves idea, there's a lot more evidence out there that also backs up this picture, that there are tons of mass. There's a whole lot of missing mass out there that we have never seen before. And I'm not going to go through these things very carefully, but this comes from very precise measurements of, for example, the cosmic microwave background, which is essentially the leftover light that was present in the early universe, as well as our understanding of how galaxies should form in our universe. The fact that that galaxies form in a certain way tell you that there must be additional gravitational pull, and this also is evidence for the existence of dark matter, as well as the bullet cluster, which is also very powerful evidence for something that's missing. Okay, so as in the case of Neptune, we know from its gravitational effects that dark matter is out there. In fact, all of its gravitational effects paint a very consistent picture. They tell you that they basically point towards the same thing, that there is this missing mass, and it really forms something like an invisible halo around our galaxy. And just like when we were looking at Neptune, the next thing that we want to do now is to go find it, figure out what dark matter is, and essentially have some kind of probe that will take a picture of dark matter, essentially, that would look like this. So that's the goal, and that's the very big picture of what my thesis is about. And the way that I see the problem of looking for dark matter is that you should always start with the things that you know first. So in the case of the early astronomers, they knew about gravity, they knew how to look at stars, and they computed everything that they knew about the planets. And from there, they could then deduce the properties of the missing planet, in this case Neptune. And for us, we should do something similar as well. Okay. All right, so what exactly do we know about dark matter? The first thing that we are really, really sure about is that the dark matter abundance, the amount of dark matter there is out in the universe, is extremely well measured. And we are highly confident of the fact that dark matter actually makes up something like 85% of all matter in the universe. And the way that we know this, again, is from the observation of the cosmic microwave background that I mentioned. So this is the power spectrum of the temperature correlations in the cosmic microwave background. And if you make a plot of what are the characteristic scales at which these little spots that you see here occur, that actually tells you something about the early universe. It tells you something about how structures were forming in the early universe at the point when recombination was happening. So when you do this, you get a peak here that looks that I'm showing in black dashed lines, and then you get several peaks, and then it dabs out. And this, it turns out, is an extremely powerful constraint on the amount of dark matter there is. So if you actually increase the amount of dark matter, you get something that looks like this deep blue line here. And if you decrease the amount of dark matter, you get this purple line down here. And at the point where it matches all of these curves, that gives you this 21% of the entire universe, or this 85% number that I'm showing here. So this is something that we know the best about dark matter. Another thing that we can do is to try to look for any interactions between dark matter particles and stuff that we know of, so what we call standard model particles. Everything that I've told you about previously has to do with gravitational interactions, but we are also very interested in non-gravitational interactions. So, for example, we're looking for things like something that's similar to electromagnetic interactions or other more complicated stuff that we deal with. And the way that we generally do this is to use these three very broad classes of searches. First, if dark matter can actually interact with each other and produce standard model particles, you can actually see this in things like gamma ray satellites, balloon experiments, and so on. And this will actually show up as very high energy particles being produced across the entire sky. Another thing that you can do is to wait for dark matter particles to come and hit essentially a giant vat of gas or a giant vat of liquid. And if you keep the liquid very, very quiet, you can actually try to see if there's any amount of energy being deposited into the liquid. And based on that, you can figure out if there's any of this energy deposition coming from these dark matter particles. The final way that we can do it is to collide two standard model particles at very, very high energies, so 2 protons, 2 electrons, or rather electron-positron. And then when they collide at very high energies, you hope that you have enough energy to produce 2 dark matter particles that you can then try to look for within particle physics experiments. So this program of trying to look for these interactions has been going on for decades, and unfortunately for us, we have had no conclusive evidence of any dark matter interaction. So if we look at some of the typical, or I would say some of the exemplary results for direct detection for collider physics, collider searches of dark matter, and for indirect detection of dark matter as well, we find that so far we have not had a discovery of any such interactions. We've only been able to set various limits. So before I go on to explain, if we haven't found it, what are we going to do next? Let me just go back and tell you why, in the first place, we might be interested in looking for interactions. We can see it gravitationally, but you might ask, why in the world would we expect any kind of non-gravitational interaction? And really, the reason why is simple theoretical and experimental biases. So we have 2 examples of very important models that explain other problems within the standard model. So here we have supersymmetry, which explains things like the hierarchy problem and proposes a solution that might show up at the weak scale. And another thing that has been studied extensively is the QC axion, which can resolve the QC theta problem. And so these theories, almost as a side effect of these theories, you end up with a very good candidate for dark matter. So within supersymmetry, you get neutral and very heavy particles that interact only through the weak force, and these are excellent candidates for dark matter. And here also you end up with an axion particle that interacts very weakly with as well. And both of them can be produced at the right amount in the early universe, and so on. Another thing that we're really interested in is to look for dark matter properties, right? And one of the most basic properties that you can get is the dark matter mass. If it's made up of new particles out there, the first thing that we want to know is what mass is it? And if you only have gravitational interactions, so if you're just looking at the pool of dark matter on the stars, or if you're looking at how dark matter causes the cosmic microwave background signature, then you can really learn a very limited amount about the mass itself. You can learn some amount, but it's very difficult to pinpoint exactly where it is. But if there's a non-gravitational interaction somewhere, then the various experiments can actually pin down, the various experiments looking for some of these dark matter models can actually pin down where in this huge range of masses it might turn up. Aside from this, as I mentioned, we know a great deal about the abundance, and it turns out that if you have an interaction with the standard model, so if you have some kind of interaction that looks like this, then you can also find very natural ways to produce dark matter in the early universe. And so it could be that if you introduce some kind of non-gravitational interaction, you will also get for free a way to produce dark matter in the early universe at the correct relic abundance. And here I'm showing you 2 examples where we have freeze out, where you just put in a weak scale kind of cross section, and you get essentially the kind of relic abundance that we expect. Or if you have a very weakly interacting particle, you could also get the correct abundance through a process like freeze in. So to summarize, we've been looking for non-gravitational interactions for various reasons. We have not been able to find them. And the question then is, what else can we do? And this question is very broad. Lots of people are working on it. There there's an incredible amount of very good ideas out there. But I'll just show you some of the work that I've been doing within my thesis that tries to chip away at this problem. So the main thesis questions that I had in the last 5 years really is that if we think that there is some interaction between dark matter and the standard model, we can ask these 3 questions. How is dark matter produced in the early universe? As I've shown you, there are 2 examples of how it's produced here, and that gives you, and that's all well and good. You get, it's very well motivated and so on. But really, this doesn't exhaust the space of all the possible ways in which you could produce dark matter. And some of the new ways that people have been thinking about in more recent times actually motivates the search for dark matters at other mass ranges that people have not generally been so focused on, at least in the last few decades. And so that's very helpful in trying to think about what new search approaches might be useful, and just basically expanding our ideas, the range of ideas that we have for dark matter production. The other thing is we can ask, if such an interaction exists, how can you produce it at colliders? And this also is very well studied, especially within the experimental groups. But there are creative ways and there are interesting ways in which you could do this production as well, and I will show you one example of that. And the last thing that I'm also very interested in is how dark matter deposits energy into the standard model. And given that they do deposit energy in this way, either they scatter off standard model particles or they annihilate to produce standard model particles, how do you turn this into a search for dark matter? So that's can be classified into 2 broad categories of production and energy deposition. And really, the reason why it has been such fun in the last 5 years thinking about these problems is that you can actually solve these problems over a very, very broad range of scales. So you can start from, experiments that can fit on a table, on top of a table, which is roughly 2 meters. And you can think about searches at colliders, which is roughly 20 meters or so. And then you can also think about the entire cosmos, which is something like 10 to the 26 meters. And at all of these scales, there are interesting things to be said about dark matter searches and about dark matter energy deposition and so on. So this is just a summary of all the things that I've been working on. And for this talk, I will just focus mainly on the cosmic scales, where we're looking at dark matter annihilation or decay in the early universe, depositing the energy across the entire cosmos, and figuring out what kinds of signatures we will get, and how to interpret that as constraints on dark matter or turn that into a search for dark matter. Before I go on to these 3 papers here, I'll just briefly run through the other 3 as well, just for completeness, I guess. The first thing that one of the first sort of fully particle physics projects that I worked on here was a new way of producing dark matter in the early universe. This is work done together with Jim Klein, Tracy, and Wei Xue. And like I said, in the conventional understanding of dark matter production in the early universe, how do you get the correct, that 85% number in the universe? People have been looking at annihilations. So you have 2 dark matter particles that annihilate to 2 standard model particles, and figuring out what kind of signatures and what kind of production you can get from such processes. But in this paper, what we realized was that even in a very simple model, so in this, if we look at the dark photon model, you can actually get very interesting variations on the usual freeze-out process. So the usual 2-to-2 process here can actually turn out to be not so relevant, and even things like two dark matter particles annihilating to 2 dark photons may not be the most relevant process here. But instead, the freeze-out is dominated by things like 3-to-2 annihilations. So typically, you would expect 3-to-2 processes to be suppressed relative to these processes, because you need 3 dark matter particles to come together to do the annihilation. But if you have the correct kinematics, where you have dark matter particles that are between, in this mass range with respect to the dark photon, these 3 to 2 processes can actually control the way dark matter gets produced in the early universe. And so this is an example of how dark matter gets produced. You want to essentially produce the relic density, which is that 85% number that I talked about earlier. And if you put this model in the dark photon model, and you just compute what kind of relic abundance you would get based on just this process, which is typically the one that's considered, you would get this line here, this dashed line here. But the correct answer actually, if you include the 3 to 2 process, is this red line here. And this gives you some interesting motivation for things like sub-GeV dark matter. So lighter dark matter that people have generally not been so focused on. And these kinds of models can also solve some well-known problems called the small-scale structure problems because of the large self-interaction that you generally need.
Can you briefly say what the link is between this scenario and it being the sub-GeV scale?
Right. So the link is that when you have a 3 to 2 annihilation, you have a different dependence on the annihilation rate compared to the traditional case where you're looking at 2 to 2. And because of the 3 to 2 case, the rate at which annihilation occurs scales as something like n dark matter squared instead of the usual n dark matter. And if you go through the calculations for how the relic abundance depends on how the relic abundance is actually determined based on these 3 to 2 interactions, you come up with a scale that's given by something like T matter radiation equality squared m blank to the 1/3 for the natural mass scale of the dark matter that you need, and that turns out to be sub-GeV. And this is a general characteristic of models that use 3 to 2 annihilations, including the strongly interacting massive particles, SIBs. Okay, yeah. Also, another question that I thought about briefly was how do you get dark matter to be produced at colliders? And generally, people who are looking for dark matter at colliders are looking, like in the most simplest case, you would be looking for dark matter production in these 2 modes. In other words, you have 2 protons that collide, and they go through some kind of vector mediator and it produces 2 dark matter particles. You can't see this in a collider because these are very weakly interacting dark matter particles, which is the reason why we have not seen them today. And so these will just stream out of your detector. But if along the way you have some kind of initial state radiation here that produces something that we can see, the signature that you get is a very strong energy deposition in your detector on one side due to the X, and then something that's missing on the other side. So you get a momentum imbalance, a transverse momentum imbalance in your experiment. So this is a very characteristic signature of the production of very weakly interacting particles. So this is something that we typically call the Mona X search, and this is deployed at the LHC to look for dark matter particles. Another thing that you can do is to say, if there is some kind of vector mediator between the dark matter and the standard model, then you can produce the vector mediator when you collide 2 protons. And then this vector mediator, you produce it on resonance, and it decays into 2 quarks or 2 leptons. Then you can see this as a dilepton or a dijet signature at the LHC. And that's also a very clean search for a new resonance that might be a mediator to the dark sector. What we figured out in this paper was that if you have a dark sector that has bound states, so in other words, you have 2 dark matter particles that can actually exchange some kind of scalar or vector that can keep it within a bound state, then you can actually also produce these bound states resonantly in the collider. And then these bound states then can go back into 2 leptons or 2 jets. And you can again do a dilepton dijet search for a new resonance. So why might you want to do this? It turns out if you compare where you're sensitive to either the vector mediator or the dark matter in terms of these searches, it turns out that the Mono X searches and the vector resonance searches tend to look something like this on the dark matter mass and vector mediator mass space. And the reason is because, for example, for the vector resonance case, you want to produce the vector resonance, and then it has to go back to a dijet or a dilepton signature. And so if instead it could decay into two dark matter particles, so if the V could go back to chi and pi bar, then you would not see the dijet and the dilepton signatures at the LHC, but you wouldn't be able to do these kinds of searches. And that happens when you're in this space. So in this space here, when your MV is much heavier, it's heavier than 2 times your M pi, generally your vector resonance search is not going to be useful. And so searches for bound states, at least in models where your bound state goes back predominantly to either 2 quarks or 2 leptons, can actually cover a space that looks something like this. And this actually helps you extend the reach of current searches, at least in such models. So this is something that I worked on with Gilia Law, Tracy, and Yotam Sarek. Moving on to energy deposition. This is a really interesting project where we try to build a tabletop size experiment, or at least it's the first step, build a tabletop size experiment that can be used to search for axions. And so axions are pseudoscalar particles, very light particles that behave like a classical field, and it's also a dark matter candidate. So you can imagine that there's this classical field everywhere in the universe behaving as a dark matter particle, and because of its interaction, the expected interaction between axions and electromagnetism, as light propagates through a vacuum, light in a certain polarization, let's say a horizontal polarization with a frequency omega naught, actually ends up oscillating into a vertical polarization at either omega naught plus the axion mass or omega naught minus the axion mass. And as it propagates, this kind of oscillation continues, and you get energy deposition into orthogonal polarizations with the different frequencies, into different frequencies that you might not have expected if the axion wasn't there. And so this behavior, this fact that you get energy deposition into modes that you don't expect, motivates a search for just the spontaneous generation of light in an orthogonal polarization at these frequencies. So what do? We make use of interferometric techniques. You put in a laser into some kind of cavity that can be tuned so that it is resonant at some laser carrier frequency omega naught in horizontal polarization, and also at the same time is resonant at omega naught plus minus MA in the vertical. And it turns out that you can do this with a bow tie light cavity, so with 4 mirrors and having the light bounce in this pattern. And then you can actually adjust what MA you are sensitive to by rotating these mirrors. And so you have a cavity, you rotate the mirror slightly, and if you see a resonance in the vertical generated by light coming in from the horizontal, which is an extremely unexpected behavior, if not for the axion, then you would take that as a signal for an axion being present. And if we look at what kind of search, what kind of sensitivity we can get to in the axion parameter space, you can see even with a 2 meter size experiment, so a tabletop size experiment, you would be able to cut into new parameter space in terms of the coupling between the axion and electromagnetism. So this was work done with Jesse, Cody Elwood, and Matt Evans. It was a really fun introduction to optics as well as to axion physics. Okay, so that was a very brief run through of 3 of my projects, and now I'll spend some more time talking about dark matter energy deposition in the early universe. And so I'll just start with a punchline. Again, if you think that there is an interaction between dark matter and the standard model, then every time you have dark matter meeting another dark matter particle, it could annihilate into standard model things, such as electrons or high energy photons. And these electrons or high energy photons stream across the universe And at some point, they might bump into hydrogen atoms, and they might hit one of the electrons, causing it to ionize the hydrogen atom, or it might just bump into charged particles in the first place, depositing its energy and heating up the gas in the universe. And so the punchline is that you have energy injection from dark matter, and this can affect how ionized the universe is or how hot the universe is. So these are just some examples of how the ionization levels might change as a function of time, a function of redshift, as you have dark matter annihilation or some kind of dark matter decay going on. Right. And so how do we turn this into some kind of search? How do we turn this into some kind of constraint on dark matter properties? And the way we do it is to understand what the baseline history should be very, very well. If we know what the baseline history is without any dark matter particles being present, just regular hydrogen atoms, the cosmic microwave background, and free electrons and protons. If we know this very well, and we can actually measure what the temperature is, then we can start to look for deviations from the baseline, and then this will become an important way to set constraints on the behavior of dark matter in our universe. So this kind of thinking, I think, is extremely interesting, and there's a lot of work that still needs to be done. But just to briefly go through some of the work that was done as part of this thesis, these are example temperature histories and ionization histories that you get, including dark matter annihilation or dark matter decay. And so you can see here, this is what you would expect without any dark matter, and this is what you expect from annihilation and decay. And you can see a large deviation here in the temperature. The first question we could ask is, how do we actually compute these histories? Like, how do we know that this is the correct curve that you would get when you include these effects? And can these calculations be proved? So there's been a ton of work on this stuff over the last easily 10, 15 years. But it turns out that some improvements still can be made. And you can actually, and I'll talk more about this at the end of the presentation. The second question you could ask is, if there were such deviations between the case wave annihilation and decay and the baseline, for example, here we have a temperature deviation from the baseline at a redshift of about 10. Is there any way that we can measure the temperature here? If we could measure it, for example, and we could see that the temperature was actually at this point, then we know that such a process would basically have been impossible. And so this is a very useful way of constraining what dark matter is doing in the early universe. And it turns out that you can actually make a measurement of the temperature at this point, which is pretty amazing. And you can do this using something that I will go through very briefly called 21CN cosmology. The last thing is, it also contributes significantly to ionization. And so you can see that the ionization levels increase as you go towards the present day. And we also know that at this point, stars start getting formed, and we would expect a large increase in the ionization levels anyway. And it's an interesting question to ask. When stars are forming, they ionize the universe. Could dark matter also do the same? Could they contribute very significantly to the process of reionization? So these are three questions, and they were turned essentially into three papers that are published over the years. The first one that I'll briefly go through is the question of dark matter and reionization. So as I said earlier, this is a very brief history of the universe. At very early times after recombination, the universe was mostly neutral. And then when the first stars and the first galaxies start appearing, these objects start to emit ionizing radiation, and this ionizes the universe and also heats up the entire universe. And we know that at a redshift of about 6, the entire universe is completely ionized at this point. And so the question that we want to know is, can dark matter annihilation and decay contribute in any significant way to this process? And the answer is, it's generally pretty difficult. So this is an example plot of how a decaying dark matter candidate, so you have some dark matter decays into E plus E minus, with a mass of about 100 MeV, and a decay lifetime that was picked to be consistent at that point with all known experimental constraints. And you can see here, this is a plot of the ionization history. It starts off completely ionized, and then dark matter decay actually brings you up to about a 10% or 20% ionization level at the point where the ionization was complete. And so in this case, the decaying dark matter model here can contribute something like 20% of the free electron fraction at the point of reionization. So this is an example where it might work, but if you look across the board for all of these possible, if you vary across all of the dark matter masses, and we look at annihilation processes that are S wave or P wave, and we also make sure that the cross sections that you choose are consistent with the experimental results, you find that in these two cases, you're only going to be able to produce something like a 1% contribution to the free electron fraction. And only in the case of decays, if you are within the 100 MeV to GeV range, you might get up to something like 10 to 30% contribution. So this is kind of like a more exhaustive answer to whether dark matter can contribute to reionization, and this is work done with Tracy and Jesus Zavala. And the answer is maybe, but generally hard. Okay, the next thing that we looked at is what 21 cm cosmology can tell you about dark matter processes. So this is essentially looking at measurements at this point, where you might be able to see deviations from expectation. So I won't go through the details of 21 cm cosmology, but essentially what you do is you set up an antenna, you look up into the sky, and you measure the frequency, you measure the radiation that you see in space coming from far away at wavelengths around 21 centimeters. And what this tells you essentially is how hot or how cold hydrogen atoms are at various points in time. So that actually gets turned into a temperature measurement. So for example, naively, this would be something like a picture of the sky as you scan across various wavelengths around 21 cm. And at some points, you will see that the 21 cm radiation that you expect actually gets absorbed more than you expect relative to the CMB intensity. And that's telling you that the hydrogen gas at that time is actually colder. And then at some point, you see excess radiation compared to the cosmic microwave background, and that's telling you that it's actually hotter than you expect. And that's a terrible summary because I'm sweeping a lot of physics under the carpet. But essentially, it's a temperature measurement, and it constrains the ratio of what the baryons are at, Tm, compared to the 21 cm radiation temperature, which is typically taken to be the CMB temperature. So you get a constraint on Tm over Tr. The wonderful thing about this 21 cm result is that we are right now at the point where people are just beginning to be able to measure it. It's fiendishly difficult to actually measure this well. But last year, one experiment, the EDGES experiment, actually reported a measurement of the 21 cm radiation. And it was quite a stunning result because what they observed was actually that 21 cm radiation was absorbed much more strongly than expected. So this is where we expected it to be. And this is what's actually seen. And what this tells you is that the matter temperature that we expected was somewhere here, based on the baseline histories that I showed you earlier. But the EDGES experiment actually measured something that was way lower, which means that there's some new effect. I mean, if we were to take this experimental result seriously, what this means is that there's some new effect present that is actually bringing the temperature down to what EDGES actually observed. So what we did was we went through the literature and we made a list of all the possible effects that could be at play to explain this result. And some of the things that we came up with was, for example, if the 21 cm radiation that you observe is actually brighter than you think it is. So for example, instead of just the cosmic microwave background, which is at a temperature of about 50 to 60 kelvins, imagine if there was an additional source of 21 cm radiation that actually brought the radiation temperature up to about 100 kelvins. That would actually be able to explain the deep absorption that you saw earlier. So we took all of these possible new physics effects, and then we said, if we include each of these new physics effects, like an additional 31 cm source, or another approach is to get non-standard recombination, what kinds of constraints can we get on decaying dark matter or annihilating dark matter? So in this case, I'm showing you a plot of decaying dark matter to E plus E minus, and the constraints that you can get, assuming one of these novel scenarios. And you can see that it actually outperforms state-of-the-art constraints. So for example, the Planck CMB limit on decay, on the minimum decay lifetime for chi to E plus E minus is somewhere in the 10 to the 25 seconds range for 100 MeV particle. But this kind of approach where you take the global 31 cm signal actually pushes you up 2 orders of magnitude. And so I think this whole edges result and what's happening there is still very unclear. But from our perspective, what is very clear is that in the future, when this picture of the 21 cm result clears up, we can actually use these global signal measurements to really push the constraints up and to do much better than what we have right now. And yeah, I forgot to mention that this, I didn't put it up here, but this was work done in collaboration with Tracy last year. And finally, we come to, are we actually doing these calculations correctly? Are we actually sure that this is the line that you would get if you put in some S-wave annihilation model or decay? And so for that, we have to dig into the horrible details of how you actually do these calculations. First, the baseline history, which is what you would expect with just hydrogen, just electrons, just free electrons, free protons, and photons from the cosmic microwave background. It turns out that this is a very well understood problem. Starting from the 60s, people already had something that was correct to within 10%. And today we have recombination codes that actually tell you what the ionization history should be and what the temperature history should be, down to a level of about 0.1% or better. And it's actually pretty simple physics, which is really cool. You just take the hydrogen atom, you just take n equals 1 and the two n equals 2 states, and all other states you assume to be in equilibrium with n equals infinity state, which turns out to be a good approximation. And then you couple this to the CMB. And when you do that, you get these two equations, you solve them, you get these two curves. And yeah, the baseline that you get tells you that in the early universe, you're fully ionized. At some point, you undergo recombination. And then today, you have an ionization level of 10 to the minus 4. And then the temperature history says that the gas temperature, at least without any stars or galaxies, should be something like 1 to 10 Kelvin in the 10 to 20 redshift range. What happens when you add dark matter and energy injection? Dark matter then acts as an additional source of heating or ionization. And you can add these terms in here, which are just proportional to the rate at which energy is being injected, multiplied by some factor that we call F. And this F essentially characterizes how the energy is being deposited. The main thing to note here is that whenever you have some dark matter process that injects energy, not all of it gets deposited immediately into the gas, because it might produce particles that free stream in the universe for a very long time before it actually interacts with the gas at all. And so all of that is just condensed into these three factors here: F heat, F ion, and F excitation. And all of these are very non-trivial to calculate, but a lot of work has been done, including by Tracy, to figure this out. And this is where these curves come from, these Fs. So, I mean, if that was the end of the story, then yes, we would have calculated these energy deposition curves accurately. But it turns out that it's not quite. And the reason is because these Fs also actually depend not just on the redshift at which you're at, but also on the ionization level of the universe at that time. And all of the previous work that I showed you calculated these Fs as a function of Z, assuming the baseline ionization history. So in other words, assuming this blue curve here. But as you can see, when you put in energy deposition, you're going to get strong deviations from the blue curve, the baseline. because of the energy deposition processes. And you might get, even 2 orders of magnitude difference, and this actually affects the whole energy deposition process significantly. So to put it another way, there's a non-trivial back reaction from the fact that ionization is increasing as you deposit energy. And so as the ionization level increases, it affects the subsequent deposition. And so you get this sort of this positive feedback between energy deposition and increasing ionization level. And in some cases, when you increase the ionization level, you actually increase the rate of energy deposition. And so this feedback loop can be important to take into account. Also, if you compute these Fs without any X of E dependence, so just a Z dependence, there's no way that you can put in reionization at all, right? Because reionization is ionization coming from stars and galaxies and so on, and that's going to increase your ionization levels up to 1 essentially. So at that point, you need to compute these Fs, taking into account the fact that your X of E's are increasing. So what we did, and this was work done in collaboration with Greg and Tracy, was to actually compute these Fs, taking into account the changing X of E's. Again, this is gory details that I'm going to skip right now. But the point is, you have some kind of injected particle, you compute the stuff that gets deposited, you compute the Fs, you compute the ionization and temperature, and then you feed this back in to compute the result in the next step. And in this way, essentially previous calculations didn't have this arrow, and now we're just including the arrow, we're doing it in a smarter way than before, so that these calculations proceed quickly and efficiently. And so this is the code structure that I'm just going to skip at this point.
We did start 10 minutes late, so.
It's true.
I mean, if you need a bit more, it's fine if we finish.
Okay. Well, I mean, I think it's very boring, so I'm just going to skip it. Yeah.
It's completely up to you.
Yeah,
But we
okay.
did start 10 minutes.
Yeah. So with that code, now you can get self-consistent calculations of energy deposition. And so this is an example of what happens when you include back reaction compared to the previous calculation without any back reaction. So if we just look at the matter temperature, this is the baseline that you would get with no dark matter. Now I'm putting in a dark matter decay model to E plus E minus with these parameters. And in the original calculation, you would get this curve here in blue. And that was assuming the baseline ionization level, which is this ionization level shown here in the black dashed line on the right. So you get this curve, but what happens when you do the calculation consistently? In other words, as you go along and you integrate the results, you make use of this curve instead, the curve here that is in orange. Then the energy deposition into heating is actually significantly higher, and you would get an increase in the actual matter temperature that you would calculate. And in some cases, for example, if you look at really low redshifts, like a redshift of 10 to 20, you could get something like factors of 2 to 3, and it gets worse as you go along. The main reason why this happens is because as your ionization level increases, you have a ton more charged particles flying around. And so anything that gets deposited, anything that gets injected by this dark matter decay sees a lot more charged particles than you thought. And this means that it can scatter through Coulomb interactions much more efficiently compared to what you thought it was previously. And this leads to a significant amount of heating at late times. And this is very important for all the late time signatures that I showed you earlier. So things like reionization as well as 21 cm may have a big effect. It may have a big effect on these things. Right, so this is one plot that I'm showing here where I give you a comparison of what happens with and without back reaction and the fractional change in the temperature with and without this effect. And so I've chosen chi E plus and minus, and I've chosen the constraints set by the cosmic microwave background to set the decay lifetime as a function of mass. And if you just look at where 21 cm cosmology is sensitive to at about a redshift of 17, you just draw a horizontal line here. You can find patches of parameter space where you have something like 2 to 500% changes in the dark matter temperature. The matter temperature, or maybe just 100 to 200%, which is a factor of 2 or a factor of 3. So it's a very significant problem, and as you go further down, it becomes even more significant. So it's very important to take into account that reaction. And finally, the fact that you have a consistent calculation with the ionization level evolving and so on means that now you can put in a model for reionization. So I've chosen here a model in the black dashed lines on both plots. And then you can throw in dark matter processes as well. And then you can also compute self-consistently with the back reaction result. And you can see if you compare the plot first of all, the previous result, the only sort of consistent previous result that had been derived before this in the literature is the curve in blue. And now you can put in the dark matter, the reionization model, which is in black dashed lines. You can put in the dark matter energy injection, which gives you the green. And then if you do the full calculation self-consistently with back reaction, you get the line in red. And what this does is it opens up, first of all, a bunch of probes here. So you have a lot of measurements of the matter temperature down here. And if you could compute the dark matter annihilation effects on the matter temperature, you might be able to set constraints on these processes by using measurements down here. Where previously you could only set very conservative constraints based on just this curve, basically. As well as the fact that, when 21 cm, when the 21 cm experiments become more well established, you might be interested also in seeing deviations, in making sure that you compute your dark matter effects with a reasonable reionization model in mind, so that you actually have something that's more physically realistic compared to just this blue dash line here. So we have put all of these tools into a single code called Dark History. We think it's reasonably easy to use, although the transfer functions are huge, gigabytes. We're working on trying to cut that down, and it's got documentation, and we think you could get some of these curves that I showed you earlier essentially just by one line in the code package. And we hope that this forms a basis for future calculations of the temperature and ionization histories. Okay, so I will conclude quickly. This is sort of the landscape of the stuff that I've been spending time on over the last 5 years. I think it's really cool, and there's lots of future work to be done. There's a lot of work to be done to improve even further all of the stuff that we put into Dark History. One of the things that we hope to get is not just the ionization and temperature effects, but also what kind of CMB distortions do you get from these dark matter annihilation or decay processes. Because when you have high EV plus and minus, you're going to generate a whole bunch of photons that are below 10 EV or so, and they're just going to continue redshifting to the present day, and they might show up in CMB energy spectrum measurements. And we hope to be able to do a consistent calculation that gives you what the final spectrum is that you might expect from that. I think 21 cm cosmology is really amazing. There's a lot of new results that have come out, both from the global signal and from the power spectrum. And that's going to tell us a lot about dark matter as well. I'm really interested in realizing this experiment, the ADBC experiment. I think it's really cool, and the fact that you can just build it, on a 2-meter platform. And I mean, of course, this is because we're a really amazing LIGO physicists that know what they're doing. But the fact that you can actually do something like that on a 2 meters length scale is pretty amazing. And the last thing that I'm really interested in is any new probe for new physics. The next thing that I want to think about is whether we can see any of these low energy tails to the CMB power spectrum, and how that might be constrained using existing measurements. All right. So finally, we come to acknowledgements. First person that I definitely want to thank is Tracy. She's brilliant. As I wrote in my acknowledgements, I think she represents everything that's right about academia. And she was a really good mentor. I can't I definitely couldn't imagine doing any of this stuff when I first came in. But then she taught me, basic cosmology, and then slowly, getting me to be more independent. And yeah, it's been really fantastic, and I'm very honored to have the support. Jesse, of course, he does physics with such joy. I don't know how to describe it, but it's just very infectious. And you set the bar so high, and I wasn't directly a student, but I learned so much just from listening to you, and from the fact that you influence everyone in the CTP, and that sort of percolates down to everyone else. And so we all try to give good talks, we all try to have nice plots, we try to write well, and like everything because the bar that you set here. And I'm very thankful for your advice and for everything that you've taught me. I definitely want to give a shout out to Cornell Physics. They really are the ones that made it possible for me to imagine being here. I graduated in 2010. I started grad school in 2014. And for personal reasons, those 4 years were, I felt at least in 2010 was very hard to bridge. But these people convinced me that I could do it, and that there was a way to do it. And they made me apply in 2010. They made me visit all the schools, talk to all the professors, email them constantly, make sure that I keep in contact with everybody every 6 months. That's what they told me. Every 6 months, send an email to Krishna, who isn't here, but I'm sure he was annoyed by my spam. But they were really awesome. Jim, especially, was extremely supportive, and I learned so much about particle physics in general from him. And I'm very thankful for Jim, Chaba, Julia, as well as Freya and other collaborators other than Tracy and Jesse, Jim, Yotam, and Wei taught me so much about how to do particle physics, how to use fine calc, how to write, I like this one, how to write a referee response that will cause the referee not to open the draft. So that it saves you trouble when it comes to reviews, which is just pretty good trick. Definitely, yeah, and they were very patient about it as well, especially when I was starting out, not knowing anything about freeze up. Yeah, and then there's Greg, who without Dark History would have taken a lot longer and it would have been a lot less fun. So thank you for that. As well as definitely Brody and Matt, Jesus, Cannon, Gilly, and Stephen as well. The CTP is very amazing. I looking back, I think I couldn't be luckier in terms of how open the CTP is, how friendly it is, and how important that is to doing good physics and to learning. And so I want to thank just pointing out people who went through part 3 with me, including Jasmine, Patrick, Andrew. Andrew went through all of my classes as well, which is fun times, especially Kirky too. Grado, Julian, Ian and Lena, who are my office mates. Rebecca for being at conferences last year. Ian as well, I learned so much from him. Nick, definitely learned a lot. Chen, Sarah, and Yong. More broadly, all of the friends that I've made over the last 5 years, nice hair. People back home, people at Princeton, people at the IAS, at NYU, people here at MIT, Singaporeans here at MIT, really made the process really much easier than it would have been without your support. Yeah, I was supposed to mention this. We started a dark matter Twitter bot run by Kai-Cheng Liang. He actually wrote a Twitter bot called XenoCat that goes through the archive and does some machine learning magic and spits out all the dark matter papers for the day. I am kind of involved in the training, and he's trying to convince me to post some commentary now and then. But we'll see how that goes. But if you're interested, follow XenoCat. Finally, my family, this is my wife's family. To Liang Ying and Rick, I'm very thankful to our family in New York City. It's been great, and I'm really looking forward to the newest addition to your family, and to my parents-in-law for being very supportive throughout the last 5 years and being very welcoming as well. My own family, my parents, without you, none of this, like I would have been, none of this would have been possible at all. And I love you guys very much. My sister, Gary, my wonderful niece and nephew, Sophie and Julian. You guys have brought very great joy to me and Yangtze, and we're very happy that you guys are happy. And to my sister, you were very formative in my early years and beyond. And so thank you all for that. And finally, my thesis is dedicated to Yangtze. She has been incredibly supportive. And over the last 5 years, we got married, and it's really nice knowing that we'll be spending the rest of our lives together, whatever happens, which makes me much happier than anything that I did in this thesis. All right, thank you to all of you.
Are there any questions for the public session?
Yeah, so at the beginning of the talk, you mentioned that we see roughly 1/6 of all of the matter being visible matter.
Yeah.
And you were talking about various different ways that energy can be dumped into the visible sector.
Right.
Do you have any comments about how many distinct dark matter sectors you think there are? Like if there were hundreds of dark sectors that were all weakly coupled to one another, I would be surprised if 1/6 of all of the matter was visible.
No, that's a very good question. So I think, maybe I didn't say this well enough, but definitely the fact that the abundance of dark matter being 5 times the standard model is very intriguing, because why is it 5? It could be like 5 to the 10 to the power of 3, right? Or something like that. And that suggests that there is some interaction. I think this is probably the most powerful suggestion that there is an interaction between dark matter and standard model. For sure, people have thought about things like I think it's dynamical dark matter, where they have like a whole series of dark matter particles that could cascade into each other, and like I don't know how many particles they have, but I think it's interesting to think about how these models might play out, where you have multiple dark sectors or multiple dark matter particles. But generally, it's very hard to come up with anything like concrete, I feel, where you can actually sort of seize on that and set constraints and do experiments. Whereas these ideas are relatively clean, where you only have one candidate and you know what this should be, and you can just do a search. So I think it's a matter again of like theoretical bias, right? Like I could think of that and I could be like, okay, that's a mess, and I could do calculations maybe, but then it's just really hard to think about it. And maybe that's a blind spot, but also it's just you need to do things that are tractable.
Okay, if there are no further questions, let's go to the closed session. Thank you all very much for coming.
Thank you.